There is a peculiar honesty in the way nature resists being neatly packaged, and nowhere is this more apparent than in the uneasy truce between quantum theory and the geometry of space and time. Einstein sensed this tension early on. He did not deny the predictive power of quantum mechanics, yet he suspected that its success concealed an incompleteness, not of calculation, but of understanding. What troubled him was not randomness itself, but the absence of a coherent picture of reality that could sit comfortably alongside the smooth causal structure demanded by relativity. Quantum theory, as it is usually taught, thrives on abstraction. States exist in a mathematical space that bears little resemblance to the physical world we inhabit, and measurement arrives as an almost magical intervention. Before observation, the system is said to exist in a superposition. Afterward, it chooses. This choice, however, is never explained in terms of physical law. It is merely declared. Einstein saw that this was not a minor philosophical discomfort, but a structural gap, a place where the theory quietly steps outside its own rules. Relativity, by contrast, is deeply geometric. It insists that physical reality is encoded in the curvature of space-time itself, that cause and effect are woven into the shape of the universe. There is no external observer here, no privileged moment when the equations politely stop and ask a question. Everything that happens is part of the same continuous fabric. The clash with quantum mechanics is therefore not surprising. One theory demands completeness and objectivity, the other survives by postponing both. The hidden gap lies precisely at this boundary. We assume that quantum linearity must hold at all scales, even when gravity becomes significant, even when space-time itself is no longer a passive stage. Yet gravity is not just another force. It defines what it means for events to be separated, for clocks to tick, for reality to be local at all. To apply quantum superposition to radically different space-time geometries, without consequence, may be mathematically convenient, but it is physically audacious. Einstein's instinct was that a deeper theory would restore an objective description, not by abandoning quantum principles, but by refining them. The universe, after all, does not wait for measurements to decide what it is doing. There must be a process, subtle and as yet unseen, by which potentiality gives way to actuality, governed not by human intervention, but by the internal consistency of nature itself. If such a process exists, it would not announce itself loudly. It would appear as a tiny deviation, a place where perfect symmetry quietly fails, where probability is nudged by structure. We have grown accustomed to thinking that randomness is fundamental, but it may instead be a shadow cast by a theory that has not yet learned how to include gravity without tearing its own fabric. The truth Einstein glimpsed was not a rejection of quantum mechanics, but a warning that its current form may be provisional, a remarkably accurate map that omits a crucial dimension. And until that missing piece is acknowledged, our picture of reality will remain exquisitely precise and profoundly incomplete. Einstein's unease with quantum mechanics has often been reduced to a caricature, as though he were merely nostalgic for determinism or unwilling to accept probability as a feature of the world. This reading misses the depth of his concern. He was not arguing against the extraordinary numerical success of the theory, nor was he blind to its experimental triumphs. What unsettled him was something far more fundamental, the question of what the theory was actually saying about reality itself. A physical theory, in his view, should not only tell us what we will observe, but should also offer a coherent account of what exists independently of observation. Quantum mechanics, as it is usually framed, stops short of this demand. It provides a mathematical object that evolves smoothly and predictably, yet the moment we attempt to relate this object to the physical world, the story changes abruptly. The evolution is interrupted, replaced by an event that is not described by the same rules. The system is said to collapse. But this word conceals more than it reveals. It does not describe a physical process unfolding in time, but a formal update in our description, as though reality itself was secondary to our knowledge of it. Einstein found this deeply troubling because it blurred the boundary between physics and epistemology. The equations appeared to speak not about the world, but about our expectations of measurement outcomes. This subtle shift carries enormous consequences. If a theory only accounts for what observers will see, then the observer becomes an essential component of the laws of nature. Yet the universe existed long before observers emerged, and it continues to operate in regions forever inaccessible to measurement. A satisfactory physical theory, Einstein believed, must apply equally to all of reality, not merely to the thin slice illuminated by experimental intervention. There is also a deeper structural worry hidden here. In classical theories, even probabilistic ones, uncertainty reflects ignorance about underlying facts. In quantum mechanics, uncertainty is elevated to a principle, and the underlying facts are declared non-existent or undefined. This move may be mathematically consistent, but it leaves unanswered the question of how a definite world arises at all. Tables are solid, stars follow trajectories, and events occur in a definite order. To say that these features emerge only at the moment of observation is to replace explanation with postponement. Einstein's dissatisfaction was therefore not a rejection of modern physics, but an insistence on its completion. He suspected that quantum mechanics, remarkable though it was, functioned like a provisional language, powerful in practice, yet incomplete in meaning. The theory worked because it captured something true, but it gestured toward a deeper level of description that had not yet been articulated. The discomfort he felt was the discomfort of a geometer confronting a map that predicts distances flawlessly while refusing to say what space itself really is. Quantum mechanics presents itself as a rigorously defined mathematical structure, yet at its core lies a quiet discontinuity that is rarely confronted directly. The equations governing the evolution of a quantum system are precise, linear, and deterministic. Given a state at one moment, the formalism tells us exactly how it will evolve at the next. This evolution unfolds smoothly in time, respecting the internal logic of the theory, and then, without warning, this logic is suspended. When a measurement is said to occur, the continuous evolution is replaced by a sudden jump, a selection of one outcome from many possibilities, governed not by the same equations, but by an additional rule. This rule is not derived from the underlying dynamics, it is appended. The theory instructs us to apply one set of laws when no measurement is taking place, and an entirely different prescription when one is. What counts as a measurement, however, is never clearly defined. Is it a macroscopic device, a conscious observer, an irreversible interaction, or merely an increase in complexity? The theory remains silent, and this silence is not accidental. It is the mark of an unresolved tension embedded within the framework itself. The difficulty is often dismissed as philosophical, but it is in fact profoundly physical. A physical theory should not depend on vaguely defined external interventions to function. Yet quantum mechanics does exactly this. It draws an invisible line between the quantum and the classical, between the system being observed and the apparatus doing the observing, without explaining how or why such a division should exist. The equations work impeccably as long as this boundary is respected, but they offer no guidance for where it ought to be placed. This creates a peculiar situation in which the most fundamental theory of matter relies on concepts that are not themselves fundamental. Measurement devices are treated as classical, even though they are composed of quantum constituents. The collapse of the quantum state is said to occur when the system interacts with something sufficiently macroscopic, yet macroscopic objects are precisely what the theory should be explaining, not presupposing. The explanation thus circles back on itself, using the outcome to justify the process that supposedly produced it. The deeper issue is that the collapse is not described as a physical event unfolding in space-time. It has no duration, no mechanism, and no location. It is an update to our description, not a change in the world. This invites the unsettling interpretation that reality itself is somehow secondary to observation, that the universe waits in a suspended state of possibility until interrogated. Such a view may be operationally convenient, but it sits uneasily with the idea of an objective external world. If the laws of physics truly cease to apply at the moment when they are most needed, then something essential is missing. Either the collapse is an approximation to a deeper process not yet understood, or the theory is incomplete in a fundamental way. To accept the break without explanation is to accept that our most successful physical theory contains an exception at its very heart, a place where calculation continues but understanding quietly stops. Relativity rests on a deceptively simple demand. The laws of physics must look the same to all observers, no matter how they move. This principle is not a technical convenience, but a statement about reality itself. There is no preferred vantage point from which the universe reveals its true nature. Space and time are not passive backgrounds, but active participants, shaped by matter and energy, dictating what can influence what, and in what order. Causality is not imposed from outside, it is built into the geometry of space-time. Within this framework, the notion of an external observer becomes deeply problematic. An observer is just another physical system, subject to the same laws, embedded in the same space-time fabric. There is no place to stand outside the universe and watch it unfold. Events occur whether or not they are observed, and their relationships are fixed by the causal structure of space-time, not by acts of measurement. This is one of the great conceptual achievements of relativity. It removes the human perspective from the foundations of physics. Quantum mechanics, however, reintroduces this perspective in a subtle but profound way. The formalism assigns a special role to observation, treating it as the moment when possibilities crystallize into facts. Before measurement, the system is described as a superposition of alternatives. After measurement, only one remains. This transition is not described as a physical interaction between systems governed by space-time geometry, but as a conceptual shift tied to observation itself. The observer, once banished, quietly returns. The tension becomes unavoidable when one asks a simple question: whose observation counts? In relativity, different observers can disagree about the order of events, yet all descriptions are equally valid. There is no universal now slicing the universe into past and future. If quantum collapse is tied to observation, then at what space-time location does it occur? Different observers may not even agree on the temporal sequence of measurement events, yet the theory demands a definite outcome. The clean geometric consistency of relativity begins to fray. Attempts to reconcile this often invoke classical measuring devices as anchors of definiteness. But this only postpones the problem. Classical objects exist within space-time and obey relativistic constraints, yet their supposed classicality is never derived from quantum principles. The division between observer and observed becomes frame-dependent, arbitrary, and ultimately incompatible with the theory that denies privileged frames. Relativity suggests that reality is a four-dimensional structure, a complete tapestry of events laid out in space-time. Quantum mechanics, in its standard interpretation, treats reality as something that is continually updated, as though the tapestry were being rewoven each time an observation is made. These pictures are not merely different in emphasis, they point in opposite conceptual directions. If space-time itself has no external observer, then neither should the laws that govern it. Any fundamental account of nature must describe processes that occur objectively, whether or not they are registered by a measuring device. The lingering dependence of quantum mechanics on observation is therefore not a philosophical curiosity, but a signal that its foundations may be misaligned with the geometric demands of relativity, leaving a fault line that runs through our deepest description of the universe. Gravity occupies a peculiar position in our understanding of nature. Unlike other forces, it does not merely act within space and time, but defines their very structure. To speak of gravity is to speak of geometry, of how distances are measured and how clocks tick. This makes it fundamentally different from electromagnetism or the nuclear forces, which operate against a fixed background. Gravity is the background, and this distinction becomes crucial when one attempts to treat it in the same quantum language as everything else. Quantum theory is built on superposition, the idea that a system can exist in multiple states simultaneously until a definite outcome emerges. Applied to particles or fields on a fixed spacetime, this idea has proven extraordinarily successful. But when the system in question is spacetime itself, the meaning of superposition becomes obscure. A superposition of different gravitational fields is a superposition of different geometries, each defining its own notion of distance, time, and causality. To place these geometries into a single linear combination is not merely counterintuitive, it raises the question of how physical processes are to be compared across incompatible notions of spacetime. The difficulty is often masked by mathematical formalism. One writes down equations, quantizes variables, and proceeds as though the conceptual foundations were secure. Yet beneath the symbols lies an unresolved tension. If space-time geometry determines what it means for events to be separated or simultaneous, then a superposition of geometries undermines the very framework needed to define quantum states and their evolution. The theory begins to rely on structures that it is simultaneously placing into uncertainty. This suggests that gravity may resist quantization in the straightforward manner applied to other forces, not because quantum mechanics is wrong, but because its assumptions may be incomplete when geometry itself becomes dynamical. The linearity that underpins quantum superposition may be an approximation, valid when gravitational effects are weak, but subtly violated when differences in spacetime curvature become significant. Such violations would be tiny, almost imperceptible, yet conceptually decisive. If gravity influences the passage of time, then different quantum alternatives associated with different mass distributions correspond to different temporal structures. Allowing them to coexist indefinitely in superposition implies a universe that cannot agree with itself about how time flows. It is not unreasonable to suspect that nature resolves this conflict through a process that suppresses such superpositions, favoring definite geometries over indefinite ones. This would not be an added rule, but an expression of gravity's unique role. Treating gravity as just another quantum field risks overlooking this distinction. The success of quantum field theory may tempt us to assume that the same strategy will always work, but history suggests otherwise. New domains often demand new principles, even when old ones remain partially valid. Gravity's resistance may therefore be a clue rather than an obstacle. If so, the path forward lies not in forcing gravity into an existing framework, but in allowing it to reshape our understanding of quantum theory itself. The deepest insights often arise when a theory encounters a limit it cannot cross without changing its own foundations, and gravity may be marking precisely such a boundary, one that points toward a more complete and subtle picture of reality. At the heart of the quantum puzzle lies the strange passage from multiplicity to singularity, from a cloud of possibilities to a single, definite event. Quantum theory describes the realm of potentiality with extraordinary precision, yet it remains curiously silent about how this potentiality resolves itself into the concrete facts of experience. Outcomes occur, records are formed, and the world presents itself as definite, but the theory treats this transition as something that simply happens, without offering a physical account of why or how it does so. The prevailing view has often been that no deeper account is required, that probability itself is fundamental, and that asking for more is a relic of classical thinking. Yet this stance leaves a crucial question unanswered. If probabilities merely encode our expectations, then what is it that the world is doing before those expectations are confirmed? To deny the existence of an underlying process is not to explain it away, but to step around it. The emergence of actuality remains an unexplained fact, perched uneasily at the edge of the formalism. There is an alternative possibility, one that takes the transition seriously as a real physical phenomenon. In this view, the reduction from many possibilities to one is not triggered by observation or awareness, but governed by objective principles. Nature itself may contain criteria that determine when a superposition can no longer be sustained, when competing alternatives give way to a single outcome. Such criteria would not replace quantum mechanics, but extend it, supplying what the current theory leaves implicit. This perspective reframes randomness in a subtle way. Outcomes may still be unpredictable in practice, yet unpredictability need not imply the absence of law. The precise motion of a falling leaf is unpredictable, but it is not lawless. Likewise, the apparent randomness of quantum events may conceal a deeper structure, one that does not restore classical determinism, but introduces a new layer of physical causation. The universe could be lawful without being rigidly predictable. The appeal of this idea lies in its objectivity. If the transition from possibility to actuality is governed by physical conditions, then it occurs whether or not an observer is present. The moon does not wait to be seen in order to exist in a definite state, nor does a distant star depend on measurement to decide its fate. Reality unfolds according to its own internal logic, and observation merely reveals what has already taken place. Such a view also aligns more naturally with the continuity of the physical world. Macroscopic definiteness would not be an inexplicable exception, but the cumulative result of countless microscopic transitions, each governed by the same underlying principles. Thus, classical world would emerge not by fiat, but by necessity, as large-scale systems exceed the thresholds that allow sustained superposition. The challenge, of course, is that any such process would be subtle, its effects drowned out by the overwhelming success of standard quantum predictions. It would reveal itself only in carefully chosen situations, where competing possibilities differ in ways that strain the underlying structure of space-time or mass energy. Yet the absence of easy detection does not imply non-existence. Many fundamental features of nature announce themselves only through delicate deviations. To seek a lawful account of how reality becomes real is not to retreat from quantum insight, but to follow it to its logical conclusion, insisting that the passage from uncertainty to fact is itself part of the physical world, governed by principles as real and objective as those that describe motion, force, and geometry. Quantum mechanics has earned its status through an almost unrivaled record of success. Its predictions are confirmed to astonishing precision, its mathematical structure is elegant, and its practical applications permeate modern technology. Yet success of this kind can be deceptive. A theory may work flawlessly within a certain domain, while still offering an incomplete account of the deeper reality it gestures toward. Accuracy alone does not guarantee completeness, and it is precisely here that a subtle but important distinction must be made. The framework of quantum mechanics functions remarkably well as a tool for calculating probabilities of outcomes. It tells us what we should expect to observe and with what likelihood, and it does so with extraordinary reliability. But in focusing so intently on prediction, it leaves open the question of description. What is the world like when it is not being measured? The theory answers this not with a picture of reality, but with a set of rules for updating expectations. This pragmatic restraint has served physics well, yet it may also conceal a missing layer of understanding. History offers many examples of theories that were both powerful and incomplete. Classical mechanics could predict planetary motion with great precision, yet it could not account for the curvature of space-time. Newton's laws were not wrong, they were limited. They formed a special case of a deeper geometric structure that only revealed itself when assumptions about space and time were re-examined. In a similar way, quantum mechanics may represent a limiting description, extraordinarily accurate within its range, but silent about the principles that underlie its most puzzling features. The sense of incompleteness does not arise from experimental failure, but from conceptual strain. The reliance on external observation, the unexplained collapse of states, and the uneasy coexistence with relativistic space-time all suggest that the theory is doing something provisional. It works because it captures essential truths, but it works around questions it cannot yet answer. This is not a flaw to be dismissed, but a signpost pointing beyond the current framework. To acknowledge incompleteness is not to diminish the achievement of quantum theory, but to take it seriously. A complete theory should explain not only how probabilities are assigned, but why the world presents itself as definite at all. It should describe processes that occur objectively, without appealing to special roles for observers or measurements. It should mesh naturally with the geometric demands of space-time, rather than sitting alongside them in uneasy coexistence. The danger lies in mistaking mathematical closure for conceptual finality. A theory can be internally consistent and empirically successful while still resting on assumptions that demand revision. Quantum mechanics may be such a theory, awaiting a deeper synthesis that preserves its predictive power while transforming its foundations. Such a synthesis would not discard the quantum world, but recontextualize it, revealing why its strange rules arise and where they reach their limits. To stand at this boundary is not a sign of failure, but of progress. Physics advances not by clinging to its most successful ideas as untouchable, but by probing the places where they seem least comfortable. The recognition that quantum mechanics may be both profoundly correct and fundamentally unfinished keeps open the possibility that reality is richer than our current descriptions allow, and that the next step forward will emerge not from abandoning precision, but from demanding understanding to match it.